Okay, so we've been through basically two different hierarchical algorithms so far. The divisive and the agglomerative one. The first one, which is like the classical one that kind of revolutionized the research in the area, and then the faster one that gives equivalent results but much faster, the agglomerative one. And now we're gonna jump off to a completely different one, right? We're gonna talk about spectral clustering, so which is basically finding an optimal graph partitioning. So what the difference in that in this case is that we are actually not going to remove or add one edge at a time as we did before, one step at a time. We're actually going to go straight to partitioning the nodes. So we're gonna move straight in the search of the optimal groups of nodes that should be, if we were to partition the graph directly into two parts, then what are the nodes that should be in each of these two parts, right? We're gonna jump straight to that by doing a very interesting, very elegant optimization problem that I hope I am skilled enough to be able to communicate this clearly to you, because it's not the simplest thing in the world, although it is also not the most complicated. The cool thing that I personally like about this is how elegant the solution is, the modeling of the problem is, and the solution is. And I hope that you will agree with me by the end of this presentation. Now, again, graph partitioning, right? It's more or less the same as what we've been seeing before. We have an undirected graph like this. If you look at it, you can say, okay, it kind of looks like there are two communities here, right? I guess it helps that we drew it like these long edges, so it's clear that there should be like this is one community and this is another one. And the idea of graph partitioning is that we want to go straight to, okay, this is partition A and this is partition B. We don't remove one edge and then the other. We just say, this is where I cut. There's this idea of a cut, of cutting the graph, right? And the cut in this case would be basically a line over here that would simply cut these two partitions into the group A, let's say community A and community B, right? So bipartitioning or bipartitioning task, divide vertices into two disjoint groups A and B. That's the goal of the algorithm, to just go straight to that. And for now, we're going to think about this problem splitting into two. We're not going to talk about splitting into three or four like straight away. It can be done actually. As I will barely touch on it later, but it's right now we're looking at the problem of just going from one big graph down into two, right? And in this case, we would like it to be 1, 2, 3, and 4, 5, 6, as we are seeing now. But then, of course, you have to evolve the basic questions, right? The natural questions, as always. How do we define a good partition, and how can we efficiently identify such partition? We've kind of answered that a little bit before, but now I'm going to kind of take a step back, do a 180 degrees turn, and look at the problem from a different perspective, right? Well, conceptually speaking, even if we don't consider the idea of the modularity for now, one way to define what a good partition is that we want to maximize the number of within group connections and minimize the number of between group connections. Basically, if you've studied software engineering at some point, you probably came across this concept of cohesion between inside a community, right? Or let's say inside a package or something like that. Cohesion basically means that components that are inside the same group, they should be strongly connected. They should, because, or else why would they be in the same group, right? The idea of being in a group is that there is strong cohesion within the group, right? At the same time, we want to make sure that when we separate these two groups, there aren't many edges between them, because if there are many edges between them, then it's harder to partition them into groups, right? We believe that the optimal partition is that one that separates the graph into parts that are very cohesive and at the same time weakly connected between them. So in this case, it would be a cut over here, like I said in the previous slide, and that would cut this graph into two. And basically, this is just another way to think about that, right? So a cut of a graph is to express a partitioning objective is a function of the edge cut. So when I cut the graph, I get some separation, and this is like a formalization of what happens with the graph. And in this case, for example, the cut here it's very interesting. The way that it's defined here is that the cut between A and B equals the sum of the edges where I belongs to A. So like one end of the edge belongs to A, and the other end, J, belongs to B. So any edge where one end belongs to a certain partition and the other end belongs to another partition, that is part of a cut, right? And in this case, the cut is 2, because since this graph is unweighted, then each edge here simply means 1. So 1, 2. If this was weighted, if this edge had like weight 5, and this edge had weight, I don't know, 2, then the cut here would actually be 7, because the weights of the edges would be summed, right? So this is the cut of the graph. Now, one possible criterion for finding the best cut is to say, hey, let's find the minimum cut, right? Let's just minimize the cut. So let's just find a cut where we have the minimum possible sum of edges that are in two different communities, right? Because I mean that sounds like a good idea, because then the cut, the less edges are in the cut, then the weakest are the links between these two communities, and so you can cut them comfortably, right? Well, yes and no, because if you do that, then for example, this would be a minimum cut here. If you have some edge here or a node here just like laying by the side, and if you choose, okay, this is the minimum cut, this cut is 1. There are no other cuts with 1 here. Any cut that you try to do here to divide this graph into 2 will have more than 2, will be more than 2. So this is the minimum cut. But obviously that's not a good like partitioning of the graph. That would make no sense. First, because we actually know that this graph should be cut into red and green. So we know that optimal cut. And second, because it makes no sense to have one cut with one node here and lots of other nodes on the other side. Like what's the point, right? So it's not enough to just minimize it. And you will see that we find such problems usually when we're thinking about minimization and optimization, if we don't define the goals of the minimization correctly, or the goals of the optimization. We think we're setting a good goal to our objective to our optimization, and then we realize that actually no. So that's not really the right way to define the problem of the optimization here. We need to define it in such a way that we actually get this optimal cut here. And yeah, so basically the problem here is that we're not considering the internal cluster here. We're only considering the external. So I'm only saying I want to cut it in the best way possible, but I never really checked if the resulting cohesion within the communities are actually good. So both things, so you see, then what happens now is that you have two things at the same time. You have two objectives. You have the external cut and the internal cohesion. And those two must be balanced in your optimization problem. You must define your optimization problem in a way that both of them are taken at the same time. And that's what the normalized cut does. Proposed in '97, you can see this is became much before the actual Newman stuff. Newman stuff was like 2002, 2004. And this is '97, so it's about 5-7 years before that. So that's why the concept those concepts of modularity, for example, the queue, they are not really here. Like they weren't really around at this point. So you have to think of this as just another perspective. But this is still a super interesting approach, and it's not necessarily superseded by the new one. They're kind of like competitors. And basically defines that the normalized cut is not just the cut, but the cut divided by the volume of each partition. So the cut, whatever the cut you found, like that number 2, for example, that you found when you have two edges, divided by the total weight of the edges with at least one endpoint in A. So every edge that has at least one endpoint inside the community A plus the same cut divided by the sum of all the edges that are has at least one end inside the community B, which is basically just the sum of the degrees of the nodes that are within the communities. Basically, that's just it. They take every node in community A, just take the degree and sum the degree. Take every node in community B, take the degree, sum the degree. So why would you use this criterion? Well, it produces more balanced partitions, obviously, because now we're kind of like putting two things together. We want to cut, but we also want to have large volume. And you can see here that the cut here is minimized, but actually the volume here is maximized, if you think about it, because since we're dividing, when you're dividing, basically the objective turns itself around, right? Because let's say I want to minimize this thing. I want to find the minimum possible point. So at the same time, I must make sure that this is small, but at the same time, I must make sure that this is large, because dividing by a large number makes your minimization go down also very nicely. So not only this thing has to be small, but this thing and this thing, they must be large, as large as possible. So both things will happen at the same time, which is good because you want the volume of A and the volume of B to be large, right? You want the cohesion of the community to be as large as possible. But again, in the same way that we saw before, computing this thing, like if I just wanted to say, okay, I want to find this, the perfect solution, that is NP hard, which means it's just, let's say, I don't want to say impossible, I can't say that, but it's basically very hard. Very hard for any problem larger than a trivial amount of nodes, like 10 nodes or 20 nodes. Anything larger than that becomes absolutely unfeasible. It's just a very hard thing to optimize, basically. So how do we do this? And now is where we start with the actual optimization part, right? Because we want to define this as an optimization problem. And we actually did it here. Like we have a cost function, right? And every time you have a cost function, you can minimize it. So basically, let's consider that, and this is even older, as you can see here. So now it's like things are kind of like getting mixed up here because there are two different algorithms that are basically saying the same thing, but from different perspectives. And just hold it, and I will lead you away from this jungle, I promise. So now, how would we find the optimal code? Well, according to this guy, this is one idea that we could do this. We could express the partition between A and B as a vector. So what does it mean? Consider that the problem of partitioning a graph is basically assigning some labels to the nodes, right? So let's say you're gonna give a label of +1 if the node is in A, and -1 if the node is in B. So and this is what this vector is. It's just a vector of labels that has the same size as the number of nodes in your network, and then each node will get a label. It's like when you assign a cluster label to a point, right? You say, okay, this point is in cluster 1, this point is in cluster 2, and this point is in cluster 3. But in this case, we only have 2 clusters, so we're going to give them +1 and -1, right? Let's say we do this. And let's say the minimization problem here then becomes, I want to assign these labels to every node in such a way that the labels of nodes that are close together, so like in the same community, they're the same. and the label of clusters that are far away from each other, sorry, the labels of nodes that are far away from each other, they're different. So either +1 or -1. And in this sense, if you think about it, and if you look at the figure down here, in a way, this is the same as if we projected these nodes, so to speak, into a line or into a 2D, or sorry, not 2D, 1D. I'm sorry. If you project these nodes, so to speak, into a 1D space, like a one line, right? And some nodes would fall into -1, and some nodes would fall into 1. So they would be far away from each other in the line, right? And by being far away from each other in the line, if they are far away from each other in the line, then all you have to do is simply cut this line at 0, in this case, because it's -1 and +1. If you just cut this line at 0, then basically you have all the nodes in a cluster are in this side, and all the nodes in another community are in this other side. So basically that's it, you partitioned it, right? So as long as you can somehow achieve this projection or this assignment of labels in the perfect way or in the best possible way, then all you have to do is cut, and that's it. You have the partition, right? But however, we can't really do this. There's too much constraints here. Like just +1 and -1, that's too constrained, right? That's very hard. Like it doesn't give any way for working, so to speak, a little bit relaxed. It has to be relaxed, but these constraints must be relaxed a little bit, so that this optimization can actually do the work that it has to do of finding these positions. So instead of doing that, we're going to allow the epsilon values here to be the y values here. Sorry, I'm speaking Portuguese now. The y values here to take any real value. So we're still gonna project them into the line, but instead of just saying okay -1 or 1, let them just rearrange themselves, and then we'll see what happens. But the minimization problem here is this one, and I'm gonna come back to this as we go. So let's just think about this again, right? What are we trying to do here? We're going to project the nodes, so to speak. We're gonna like embed them, as people say, or project them into a line, right? A line is a 1D space. It's just a number, like you give a number to the labels. But since the assignment between -1 and 1, or just -1 and 1, this is too hard constraints to optimize. We relaxed it, and we say, okay, you know what? You can assign any label to this, as long as nodes that are close to each other in the network should be assigned labels that are close to each other. And nodes that are far away from each other in the network should be assigned labels that are far away from each other. Because that makes sense, right? That's like a remodeling of your problem in a way that similar nodes have similar values and distant nodes have distant values. You're just putting them in a line instead of putting them in a network, right? And this is what this minimization of this function here is actually telling you or modeling for you. We're saying, look, I want to find a certain vector y of labels, right? Such that if I sum the squares of these labels between I and j, such that I and j is actually an edge, so I and j are connected, right? So think about this. I have all pairs of nodes that are connected. I want the difference between the values to be minimized. So for every edge in my network, when I take the value of one and I take the value of the other end and I subtract them, I want these values to be very small. Because if they're very small, then that means that they are close together, like this. Like, for example, consider that you have a node here and you have another node here. let's say this is like 1 and or minus 2 minus 1, right? So minus 2 minus minus 1 is 1. Squared is 1. So that's a very small difference, because you're basically minus 1 plus 1 is minus 1, and then you square it, is 1. However, on the other hand, if you take like this, let's say this is minus 1, and let's say this is like 3, minus 1 minus 3 is minus 4. Minus 4 squared is 16. So the distance between this guy and this guy over here in that hypothetical case would be 16, would be very large. So they would never, they would probably never be assigned to the same community, because they're too far away from each other. So this is what we're looking for, right? This is what the minimization problem here is trying to do. Say we're again, just to restate this, we're going to put all these nodes into a line, and we're going to minimize their position in this line such that nodes that are connected by edges should end up being close together, and so that the sum here of all the differences between them is the minimum possible, right? Don't worry about this way, the way that it's written here, because I won't really get into details of how the linear algebra of this actually works, because I think it's not really the point here. The point is just that I want you guys to understand how this is an elegant way of modeling the problem as an optimization, right? And as you can see, for example, in this example here, you get lots of nodes that are very heavily connected. They end up being in one side, although there's no constraint here that this has to be minus 1 or whatever. They just end up being there because of the optimization problem. And again here, and again, of course, there's always someone who is connected between the communities, right? So there are always some edges between these communities. And this is, for example, this edge over here. Now, that said, we have established the problem as an optimization problem. And of course, now we want to minimize it, right? We say, okay, this is our cost function. The cost function is the squared error between all the nodes that are actually connected with edges. And now let's minimize it, right? Let's find the minimum of this function. Let's somehow find if we can find the global minimum, let's find the at least a local minimum. Although in this way, this is convex, so there is a global minimum here. And due to the fact that this is the minimization of a sum of squares, and there is a global solution, then we're actually going to use eigenvectors and eigenvalues to minimize it, because that's a very, very nice way to minimize convex problems like this that can be defined as a minimization of a sum of squares. And again, if you read the book and if you look at the slides from the authors, they will actually go in a lot of details on why this whole thing is what it is in terms of the eigenvectors and eigenvalues and everything. I will not do that. I will just state, without proving, that the minimization of this problem here is equivalent to finding the second minimum, the second smallest eigenvalue of the Laplacian matrix L. Okay, so let's just kind of let it sink in. There's a certain matrix called the Laplacian, which I'm going to talk about. Super simple. Don't worry about this. There's a certain matrix called Laplacian matrix, which is a simple representation of your graph. It's just like a way to represent your graph as a matrix. So you create this Laplacian matrix, then you find the eigenvalues of this matrix, which is standard operation, right? We won't go into details of that. I mean, I hope you understand what it means to extract eigenvalues and eigenvectors, because these are just requirements. I mean, I don't. It's out of the scope for this course. So you extract the eigenvalues and eigenvectors of this matrix, and then you take the second smallest one. That is the solution to your problem. That will give you exactly this line where you have to project the points or not even project them, but just, yeah, actually, let's call it that they're to projecting them. And then after you do that, you just have to cut this line somewhere, and you have two parts of the graph, and that's it, right? And I mean, this in what I'm saying here is just that the eigenvector, the corresponding eigenvector of the second smallest eigenvalue is the actual line. I mean, I was talking about the eigenvalue, and the eigenvalue is just the eigenvalue is the actual minimum sum that you get from this, and the eigenvector is the actual line that you need to project the points in order to do this. So let's take it slow. First things first, what is the Laplacian matrix, right? How do I represent my graph as a Laplacian matrix? Well, very simple. Let's start with the adjacency matrix, which is, I guess you guys are already familiar with this. If not, it's very simple. It's a matrix, it's an n by n matrix, where n is the number of nodes. So like, for example, if you have 6 nodes, then it's 6 by 6, right? You simply put a 1 if the nodes are connected and a 0 if they're not connected. So for example, well, the diagonal is always 0 because the nodes are not connected to themselves, right? So 1, 1 is 0, 2, 2 is 0, and so on. But for example, 1 and 2 is a 1 because 1 is connected to 2. So 1 and 3 is also a 1 because 1 is connected to 3. But 1 and 4 is a 0 because 1 is not connected to 4. And so on and so forth. This is a diagonal matrix, a symmetric matrix. It's a square matrix and a symmetric matrix around the diagonal because the upper triangle is the same as the lower triangle. And since it's a symmetric matrix and a square matrix, then it is, the eigenvectors are all real and are orthogonal between each other. Okay, so we have the adjacency matrix. Now, let's leave it aside for a moment, and let's then think about the degree matrix, which is maybe even simpler, right? It's again an n by n diagonal matrix. It's again square, like the adjacency matrix, almost the same. But the only thing is that the diagonal here actually has values, and outside of the diagonal, there's nothing. It's all 0. So, for example, and the values here are the actual degrees of the nodes, right? So, for example, 1, 1 is 3 because 1 has 3 is degree of 3, so it has 3 edges. Then 2, 2 is 2 because it has 2 edges. 3, 3 is 3 because it has 3 edges, and so on. It's a degree matrix, right? So just the diagonal with the degrees of each node. Nothing else. Now, that said, the Laplacian matrix is simply D minus A. So take the matrix D, subtract the matrix A. What happens? Well, you have then a matrix which again has the degrees in the diagonal, right? So all the degrees over here. And then the adjacency matrix here is actually negative. So it has 1 means that there is a connection between 1 and 2. It's exactly the same as before. It's just that it's negative. And so what happens is that then when you have this is that you basically every row here sums to 0. So since this is the degree and all the adjacencies are here, so 3 will always have like 3 here, and then there has to be minus 3 along the row here because the degree of the node is 3, so obviously it has 3 edges going out of that of it. So it has to be the rows here have to sum to 0. Now, okay, we have the Laplacian. This is, like I said, like you can see here, it's just one representation of your graph, right? Nothing else. Like it's just a way, okay, this is my graph. It has the degrees are here and the connections are here. That's it. Very simple. And like I said, what we're going to try to do here is to compute the eigenvalues and the eigenvectors of this matrix. And that's where the solution of our optimization problem is hiding, so to speak, right? And it has some properties like the eigenvalues are non-negative real numbers and the eigenvectors are real and orthogonal. This is all due to the fact that the matrix is symmetric and square and so on. So these are like very specific, let's say, easy matrices to deal with, because they give this very simple, well, not very simple, but let's say they don't really deal with imaginary numbers and things like that. So you don't have to care about like very complicated math, because they are symmetric, they are square, so it kind of like just fits in, and it's easier to extract eigenvectors and so on, because they are real and orthogonal, and the eigenvalues are non-negative real numbers and so on. And one interesting thing here is that the first smallest eigenvalue and associated eigenvector is actually, well, the eigenvector is actually a vector of ones, and the eigenvalue is 0 for that specific. So that's the smallest eigenvalue, and this has a to the fact that we defined that we wanted the second smallest eigenvalue and not the smallest, because the smallest will be this one, and this one is not a good solution to our problem. Why is it not a good solution to our problem? Because if we did consider this to be our solution, like this x over here, if we say, okay, let's minimize this by taking the smallest possible eigenvalue, yeah, sure. However, the solution that you would get is basically just ones, 1 1 1 1 1 1 1 for every node. And what is that solution? Well, that solution is the solution where we simply put every node in the same community, right? It's impossible to break a community in two here if we assign the same label to every node, because if we go back to our projection here, so to speak, if we just take every node and we put them all into one, then they're basically just all on top of each other here, around this part here. We cannot break this down into two partitions. Although in theory, this is a good partitioning, so to speak, because every node is in its own community, so there is like a very cohesive partition, but it's just one partition, right? So that's really not the solution that we want. And the reason why this thing here is a solution then is because L dot x equals 0 and so on. But it's like I said, I'm not going to go into details of how to find the eigenvectors and the eigenvalues. You can just run like for now, you can just run an extraction of eigenvectors and eigenvalues, and that should be enough for you guys to. It's more important to understand the concepts here than the actual computation of how to find this. So okay, this is a trivial eigenpair. Let's say an eigenpair is a pair of eigenvalue plus eigenvector, an associated eigenvector. This is a trivial solution, but that's not a solution we want. We actually want the second one, right? The second smallest. And why is it that the second smallest eigenvalue plus eigenvector is interesting? Because the second eigenvector is necessarily orthogonal to the first eigenvector. Because that's a definition that we had here. The eigenvectors are real and orthogonal, and that's again because of how the matrix is square and symmetric and real. So the eigenvectors, they are necessarily orthogonal to each other. So if the first eigenvector is this one, 1 1 1 1 1 1 1, then the second eigenvector has to be orthogonal to this one. And the definition of two vectors being orthogonal to each other, basically it's that the dot product between them is 0, right? So then, since I know that they're orthogonal, the first eigenvector and the second eigenvector, if I do a dot product between them, it has to be 0, right? And what does it mean that this is 0? Well, basically it just means that the sum, since this eigenvector is all just 1 1 1 1 1, then the dot product between whatever is the second eigenvector, which I don't know yet, times the first one, which is just 1, is basically just means that the sum of all the elements of the second eigenvector must sum to 0. Because again, an eigenvector dot product with 1, with a vector of ones, it's simply that eigenvector itself summed up, right? The sum of all its elements. And that must be 0. And this is where it gets interesting. Because if the sum has to be 0, then necessarily either all values are 0, right? Which is not what we want. That's not actually a valid eigenvector. But if that's not the case, then when one element of the vector is not 0, or sorry, it's positive, there must be another one that's negative to balance out so that they become 0. So for every positive element, I need another negative element that balances it in order to have this restraint that the sum of all the elements of the vector must be 0. So look at how interesting this is, because then I'm necessarily balancing out. This vector needs to find a balance between negative and positive numbers in such a way that it sums to 0. And it's what they call a 0. So it has to balance out. The balancing is part of the optimization problem. And that's why I think it's a very elegant solution to this optimization problem. Because at the end, when you run this and you find the second eigenvector, which is orthogonal to the first one, you will necessarily get a vector that has lots of negative numbers and lots of positive numbers. Basically, but not necessarily -1 and +1 like it was before. It will be like some negative elements, some positive elements, and not necessarily -1 and not necessarily equal to each other. And this is represented in this, more or less, in this drawing here. Every label of every point here, like some labels will be negative, some labels will be positive. And when we cut it right here at 0, and are basically throwing all the negative elements to one partition and all the positive elements to the other partition. And that is our graph partition. That is maximally balanced, let's say, such that this minimization problem here is solved. The reason why I cut this part here is simply because we have this constraint also that x, the solution, is a unit vector. So we know that the sum of the squares of all elements equals to 1, which happens to be this part here of the minimization, and that's just 1. So if you're dividing by 1, then it's the same as not doing anything, right? So basically the minimization is just this part here. And again, we have just solved this minimization problem where all the edges, all the endpoints of at the edges have are the closest, as closest as possible, so that this value here is minimized. So the minimization links of nodes I so that their sum is 0. Yeah, and that's it basically. So you find the second smallest eigenvalue. You find the associated eigenvector to the second smallest eigenvalue, right? So let's call it the second eigenvector, which is orthogonal to the first one, and that is your solution. And that is your solution. So you get you get this vector. This vector has a bunch of negative elements, a bunch of positive elements. And the most usual trick here is just to cut at 0. It's not the only one, but it's the most usual one. You cut at 0, and then whatever stays to the left on the negative side is part of one partition. Whatever is on the positive side is part of the other partition. And that's it. You get yourself a graph partition, which is really, really, really interesting, right? This is just a summarization of the whole stage of spectral clustering. There's this pre-processing part where we're building this Laplacian matrix, right? Which we discussed. It's just degree minus adjacency. Very simple. Then we have the decomposition step, which is to find the eigenvalues and eigenvectors of this matrix, right? And as you can see here, this, for example, these are all the eigenvalues and these are all the eigenvectors. And you can see that the first eigenvalue, as we discussed, has a magnitude of 0, and all the elements are here. They're not 1, they're just 0.4, but they're all the same anyway. So if they're all the same, then obviously it's not a good solution because all the nodes are in the same partition. And so we are taking the second one, which has the magnitude here of 1, and it has, and for example, in this case, you can see it's 3, 6, 3, and then minus 3, minus 3, minus 6. So it has to be, because it has to sum to 0, right? We have determined that it has to, right? And that's it. So we take this. These are the vertices. So map vertices to corresponding components. Basically, this is what I call like projection, right? I said it's a projection, like you're projecting the points into a line, but it's basically the same. You're just assigning values to the nodes. Node 1 gets value 0.3, node 2 gets value 0.6, node 3, and so on. And then the question of how do we find the clusters, I've already kind of like talked about it. One of the most common things is to just split at 0. Depending on the complexity of the graph, it won't always be so balanced, right? Sometimes you will have many more positive values than negative, depending on the magnitudes of the, for example, you could have one node that's like minus 0.9, and then you could have 9 nodes, positive nodes with 0.1, right? That would still sum to 0. I don't know exactly, I can't tell you exactly why that would happen, but I think that it could happen. I mean, I'm sure that it could happen in more complicated cases. This is just a stupid, simple case, but in more complicated cases, it could still happen that you don't have really a balance between negative and positive in such a way that you just cut at 0 and that's it. So sometimes you cut, for example, in the median value. So you find the median value of this vector and then cut there, because then you know that you'll have half of the nodes in one side and half of the other. That's the definition of what a median is. And you can also just like search for the best one. So you could take some of them, like take 10 different points equidistant from each other, compute the partitioning on all of them, then take like the one that gives you the best modularity, for example, or the best normalized cut, because in this case we don't have modularity. So well, we didn't at that time, but we could do that today also. So with modularity, it doesn't matter. So then there's a normalized cut in one. Then you can just like I said, you can just take 10 points and choose the one that gives you the best possible normalized cut. Because sometimes it's just not 0. You know, there are complicated graphs that are simply not that simple to cut, like the artificial ones that we've been working with. But yeah, but in this case, for example, if I cut at 0, then I would have 1, 2, 3 in one cluster and 4, 5, 6 in the other one, because these are positive and these are negative. And that's it. Yeah, these are some examples of graphs and how their spectral partitioning looks in a graph. So, for example, this graph over here, if you take the rank, well, these are the values of in x2, and x2 here is the second eigenvector x2. So, like the second shows as well, it's this guy over here, right? This one here. And then the rank is simply just an ordering of the points, and the value is the actual value. And then you can see, for example, if I take this and I order it from minimum, so from the smallest one to the largest one, and you would see that the values of this community over here, they would be all around like minus 0.25, minus 0.22, minus 0.21, then minus 0.18, so on. And then all of a sudden, boom, it jumps up to like 0.18, 0.22, and so on and so forth. So these are the labels that are assigned to these nodes here, and these are the labels that are assigned to these nodes over here. And obviously the cut here is it's just you cut at 0 and that's it, right? That's quite obvious. You cut at 0, everything that's below 0 will be in one cluster, everything that's above 0 will be in the other cluster. Same thing over here, but in this case we have 4 communities. So that kind of leads to the next question that we're going to ask, right? Because we can cut at 0 here again, and we would definitely have 2 good partitionings, because you can see here like these guys here down here, they are all over here. Then you have these guys over here, which are this community here. Then you have these guys over here, which are these community. You have these ones, which are this community. And then you cut it 0, and that gives you 2 communities. But of course, this graph actually has 4 communities. So what would you do, right? How can you, and that's the question that we're asking here. So how do we partition the graph into K clusters and not only into 2 clusters, right? And there are 2 basic approaches. I'm not going to touch into them because I think that goes out of the scope of the course. I mean, of course, you guys can take a look. These are very classic papers, again, that are, that have defined the basis of so much other stuff that we've done throughout the years. But basically, there's 2 approaches. You can recursively do the same thing that we did here. So just, okay, you cut, then you get 2 partitions. Then you take these 2 partitions and then you decompose them into eigenvectors and eigenvalues again, and just basically the same thing. Consider them as being 2 separate data sets, so to speak, and partition them again. That is for sure one possibility. But there are disadvantages here. It says it's inefficient and unstable. I won't go into details over that, but it's just simply not really like, I mean, it's kind of an obvious way to go, right? And the obvious way to go is not always the good way. A much more interesting approach is to actually take more than one eigenvector at the same time, right? Because what we did right now is just we took this one eigenvector that gave us just one value per node, right? And then we kind of like projected these nodes into this line, and they were kind of clustered together in a way that was easy to separate. But what we could do is simply build a reduced space from multiple eigenvectors. So for example, what if we get 2 eigenvectors? Then we can basically embed this network in a 2D space and not in a 1D space anymore. So we get 2 coordinates per node, right? And then we put these nodes into 2D. And after we do that, then you can cluster that. This is more commonly used in recent papers, and it's a preferable approach because usually you get better solutions, because when you embed a node into more than one dimension, they have more room to arrange themselves, let's say. And then, who knows, they could be better separated. And if you do that, then obviously you have to as well, what is the eigenvector that I should choose, right? I mean, if I started from the second one, should I take the third one or should I take the first one? For sure, you should take the third one. The first one, as we saw before, it simply puts every node in its own, in just one, on top of each other, right? And it's impossible to do anything with that. Sorry. While if you choose, for example, the third eigenvector as it is over here, this is more or less how it looks. Like, for example, the first community is over here, the second community is over here, the third community is over here, and the fourth community is over here. Now, as you can see here, this is very interesting. I can't go into details on that, but if I cut it on 0 here, then you can see how the results here would be different than this one, right? Because by cutting in over 0 here, I have basically this community and this community in the same partition, and then this community and this community in the other partition up here. But the cool thing is that if I actually use the third one and I cut it 0 at the same time, actually this community and this community would end up being put together, while this one and this one would put in another partition, which is kind of doesn't make sense. Doesn't make sense if you use it by itself. That's why we didn't take the third one by itself. We took the second one first. But if you take them both together, if you have the second one and the third one, then the combination makes sense, because then you can separate not only not only these 2 and these 2, but also within them you can separate, because then the first one and the second one are also being separated here. So you see, like, it kind of becomes a hierarchical thing, even though it's not really. But anyway, I can't go into details for that. I have said too much already for today. That's what you need to know related to the basics and the most important notions of network community detection, right? I hope that was informative. I hope that was fun. And I hope you have a good time with implementing the weekly assignment. Thank you for watching this, and see you next week. Bye-bye.